welcome to Talk Universe. This is the show for Wednesday, August 31st, 2016. And tonight we are having a very special show. We're talking about Mars. This is part one of a six-part series. And we're going to talk all about the planet and some of the things that have been discovered there. We'll talk about its history, its conditions. Then we're going to answer some questions that a lot of people have. Mars is certainly a very fascinating planet. One of the most fascinating ones in our solar system. So I decided, because so many people were interested in it, and I've done so much work on it, that a series of shows devoted to Mars and explaining what it's all about to people would be a great move. So this is what we're doing. And so this is the first installation. And tonight we're going to discuss the history and the origin of the planet, surface conditions, some things you need to know, let's say, if you're going to move there. And there's a lot of interest in that. Some people have declared, Elon Musk is one of those people, have declared they intend to retire on Mars when their day comes. And that's not unrealistic, but it would be an extremely expensive proposition considering the launch costs these days. But we'll get around to talking about that too at some point. So, what makes Mars such a fascinating planet? Well, it's certainly the most Earth-like planet in our solar system. And now understand, Venus is much, much closer in size to the Earth, and it's got about 92% of the Earth's gravity. It's just a slightly smaller planet than the Earth. But you really aren't going to make it on Venus. The atmosphere has about 90 times as much pressure as we do, and the surface temperatures run around 450 degrees centigrade. And in some areas of the atmosphere, it actually rains sulfuric acid. So, Venus isn't a vacation spot at all, and even our toughest hardware doesn't survive very well there. Mars, on the other hand, is farther from the Sun. It's the fourth planet in our solar system, with the Earth being the third, and it has some interesting properties. Over the years, people noticed that it seemed to change colors and appearance with the seasons, and we know now that at least part of that is due to the fact that there is snow, both carbon dioxide snow and water ice snow on the planet, and that comes and goes seasonally, and also that there are dust storms, and they change the color of the planet greatly. So let's get some basic facts out of the way first. How far away from the Sun, for instance, is Mars? It averages, about 136 million miles. And the thing about it is, its orbit isn't a circle, it's an ellipse, and so it varies considerably in its orbital distance from the Sun. The Earth, on the other hand, has a very small eccentricity. We stay right about 93 million miles from the Sun. That's about 148 million kilometers for the metric inclined. Mars' average is 227 million kilometers. So as a result, on the average, Mars gets a little less than half of the sunlight that the Earth does. But, as you get away from a light bulb, it doesn't change the color of the light. So the sunlight that reaches Mars is identical in color and content to the sunlight that reaches the Earth. And that's an important point to remember. When you're looking at Mars, it often has a red color or a brown color to it. And that's because the entire planet is covered with minerals and iron oxides, minerals of iron and iron oxide compounds. And that's interesting because even the Earth itself, many, many years ago, had a period of its history called the Great Rusting, when oxygen got into the atmosphere and the chemistry of sulfates in the water and of course the bloom of bacterial and single-celled life took off. And it metabolized a lot of the iron, or rusted a lot of the iron in our environment. One way or another, it all got turned into rust. Iron is very, very chemically reactive. And it's interesting to note that Mars is covered with the same sorts of oxides that we saw formed many years ago in the Earth's past. And that's another thing to think about. We have planets like Mercury, which have an awful lot of iron, and the iron isn't oxidized. It stays exactly in the same shape it was, or very close to it, many billions of years ago when it was formed. And here's another interesting point. Mars and the Earth and Venus all formed roughly the same time in the solar system from the same basic materials. So the composition, the elemental composition of the terrestrial planets, the rocky planets, is all pretty much the same in the solar system. Venus is often considered the sister planet to Earth, but that's only because of its size. Mars is a much closer match to the chemistry and the conditions that the Earth has. Now, you won't be able to breathe the atmosphere on Mars by any stretch of the imagination. It's extremely, extremely thin, about 0.6%. And for all practical purposes, for human life, it's essentially a vacuum. But there are organisms that can make it in those conditions, and a number of them have been identified in the laboratory, and some interesting experiments done with them. So, we know that Mars is a lot smaller than the Earth. The Earth outweighs it about 9 to 1. The Earth has over 9 times as much mass as Mars does. And Mars doesn't have the same composition internally. It has less iron and heavy elements inside, so it's a lighter, less dense planet a little bit. And its size, this is the interesting thing. The size of Mars is really, it's about 52%, 53% of the diameter of the Earth. So it's a little larger than half the size of the Earth. And just the same, the surface area of Mars would be about the same as the land area of the Earth. So if you were to peel it like a grape and lay it on the Earth, the surface you'd have would just about cover all the land area of the Earth, not counting oceans here. So there's plenty of land on the planet. And they've learned an awful lot about the soil chemistry from missions that have been sent there, and they've learned a lot about the geology, and this has been a fascinating study. The first successful landers on Mars were in 1976, the Viking landers, and they sent back a wealth of information, amazing things that they learned. And we've learned much more since then. We've had numerous landers. I can think of 5 right away that made it to the planet successfully, and since Viking. And some of them were mobile. Most of them were mobile, capable of driving around and getting some surveys from different areas. So we have a huge body of information. So, quickly summarized, Mars is a little more than half the size of the Earth. It's about 50% farther from the Sun than the Earth. And it has a surface gravity about 38% of what we have on the Earth. So you could leap, your center of gravity could be raised about not quite 3 times as much jumping straight into the air as you could on the Earth. And there's some interesting properties about its atmosphere that we'll get to in just a moment. So the day on Mars it's fascinating because it's so close in length to the day of the Earth. Our day is 24 hours. On Mars, it's a little over 24 hours and 39 minutes, not quite 40 minutes longer than the day on Earth. And because of that, they give it a different name. They call it a sol, after the name of the star, our sun. So, we call it a day on the Earth, and we call the rotation of Mars a sol. And again, there's not a lot of difference, but if you work on Mars time, you'll find that your days are about 40 minutes longer every time, and after a few days, you're completely out of whack. And a lot of the researchers at the Opportunity and Spirit project, when they first landed on the surface, found that it was working best for them to stay on a schedule that worked with the rovers' schedules because they were on Mars. Of course, they had to get their data when the sun was shining. And so these guys were living on Mars time, and pretty soon they were totally whacked on the calendar. But if you were to live on Mars, you really wouldn't care about that, probably. Kind of like time zones don't mess you up for the most part when you're doing business in the world. If you lived on Mars, you probably would be pretty well separated from the time clocks of the Earth anyway, and it wouldn't really matter for you. You'd live by the local time in probably most every instance. So eccentricity. What's eccentricity? As I was mentioning, the planet Mars has an orbit that changes because it's not circular. The Earth's orbit isn't circular either, but it's very, very close to circular. It's less than 2% eccentric or wobbled. For Mars, wow, it goes all the way from like 207 million kilometers to 249 million kilometers. So there's a 42 million kilometer variation from one end of the loop to the other. It's got a pretty egg-shaped orbit. It is an ellipse. And so this means that it has extremely varying amounts of sunlight during its different seasons. And it does have seasons. Now, its year is 687 days long. Ours is, of course, 365. So the Mars year is almost 2 Earth years long. And if you think about it, the periods of the seasons are also almost twice as long as they are on Earth. So just as a rule of thumb, you'd say, well, the summer lasts 6 months instead of 3 months, and you'd be pretty close to right. And so that's true for all the seasons on Mars. What's interesting, if you really look at the planet, our planet is tipped on its side slightly, 25.2 degrees. The pole of the Earth, that imaginary line that our planet spins around, is inclined over 25 degrees here on the Earth. On Mars, it's only inclined about 1.8, 1.9, and that has some very important effects on its climate. When a planet has its pole so nearly vertical, it tends to be in an ice age. That's because ice accumulating at the poles, whether it's made of carbon dioxide or water, tends to freeze and stay there. It doesn't get enough sunlight to melt and end up back in the environment. On the Earth, as our pole wobbles, we go in and out of ice ages, large swings in climate. Now, this is where our moon comes in. The Earth is fortunate. We have a large moon, and it acts almost like a balance or a countermass that keeps the axis of the Earth from wobbling severely. It keeps our climate much more stable than it would be otherwise. And on Mars, it has 2 moons, but they're tiny things, not much larger than asteroids. Some people think that they are captured asteroids, but the issue hasn't really been fully resolved. There's a lot more to know about it. But on Mars, because it does not have a big moon, its pole wobbles all over the place, and it has severe changes in its climate over the course of its year. So we can see that because of its pole shifting radically, there's nothing to stabilize it. There can be huge swings in its climate from ice ages to more clement periods. We can see that due to its orbit being so eccentric and farther from the sun, it's a colder world, and its seasons have extreme swings from one end to the other because of its extremely elliptical orbit. So it isn't a vacation spot. When you get along about to this point, you realize that survival on Mars can be difficult. But of course, we can keep people alive for a year in a submarine underwater. All it takes is power. Certainly, with the right technology, we could do the same thing on Mars. So, quick summary. Mars is a little over half the size of the Earth, has extremely thin, almost vacuum-thin atmosphere, although it does have atmosphere. It does have dust storms and weather. There is ice at the poles, and it's been found that there is a substantial quantity of water, probably enough to put 10 meters or about 33 feet over the entire planet if it were all to melt at once. But the planet appears to be in an ice age right now, and we'll talk about that just a little bit also. The planet's covered with iron oxides, so something got water on that stuff and made it oxidize, made it rust away to give it its color. And that's why it's called the red planet. So we'll get into a little more detail here very shortly, and we'll talk about some interesting things. What the soil is like, and what we've observed, and some of the spacecraft that have been there, and what they've discovered, because this is really, really interesting. A lot of people think of Mars as a potential second home for humanity, and it may be. It may be, and it's certain to happen at some point in the future. And I would love to see that. But we have some things that we need to consider if we think about moving to another planet, and Mars particularly, because it's pretty clear that it did have a lot of water in its past, and it appears to have quite a bit of water right now. And although they do claim that it's a very dry planet, overall, sure. But there are some mitigating circumstances, and we'll get into all of that very shortly.
And also, we're going to get into the foundation material that you need to know, because there's a lot about Mars that isn't being said. And this is all good science, good hard physics, all verifiable stuff. But for instance, if you wanted to plant crops on Mars, is the soil suitable? What would you need? And where will you get your water? And what do you do for radiation shielding? And all the things, the practical things you need to know. So we'll get into that in great deal of detail here shortly.
So this is Talk Universe, and we're doing part 1 of our Mars series, and we'll get right back to that material after the break. So you've just landed on Mars and you're going to step outside in your spacesuit and have a look around. What are you going to see? Now, if you land anywhere near the equator or anywhere within 45 degrees of the equator, you'll find conditions that are very different from areas near the poles. And the difference is mainly in two ways. Number one, the planet has about half of it at a lower altitude than the other half. We've picked this zero level, we'll call it. On Earth, we use sea level to reference the parts of the planet that are above the ocean and those that are sometimes in valleys that are sunken below the ocean. And on Mars, they picked an arbitrary point based on the triple point of water. It's a layer of the atmosphere or the ground level that is at the point where water could exist as solid, liquid, and gas simultaneously in that low atmosphere pressure. So half of the planet is basically below that point, and about half of it is above that point. And if you look at the map of the planet and you look at the altitude, you'll see that roughly half of it was covered in oceans in the past, and that's mostly in the northern half of the planet. And most of our landers, in fact, everyone that I know of, has landed in an area of the lowlands because they were looking for traces of what was left from the oceans or any water that might have existed in the past. So that's an important distinction. If you go to the higher territories when you make your landing, you're going to find that it's extremely arid and extremely cold, and there's an air pressure of basically less than 6 millibars, and a bar is 1 atmosphere. So if you look on an air gauge for a pump and you see bars, that's talking about how many times air pressure, Earth normal air pressure at sea level. And a millibar is 1,000th of that. So 0.6% of Earth's atmospheric pressure, or 6 millibars, is pretty typical on Mars. Now, if you're in the lowlands, you're going to see things that are a little bit different, and that is because in many of the lowland areas there are runoff channels that appear to have been created by water in the past. And in many places there are reservoirs of ice right under the soil, similar to being on a glacier with a couple inches of dirt on top of it. Another interesting distinction is this. Because there was so much water in the past on Mars, when those oceans froze or dried up, all of the salts that were present in them are left behind in the soil. The water can evaporate or freeze, but the salt stays behind. So it's like leaving a pot of water boiling on the stove, and when it boils away, the water's gone, but everything that was left in the water is left behind. So in areas that they've explored on Mars with direct contact using rovers and landers, they found that typically in these lowlands, about 20-21% of the soil tends to be salts. Now that sounds like a bad thing, but it isn't necessarily, because there are different types of salts. If it was sodium chloride, table salt, or the thing that is most common in our oceans on Earth, that would be bad for plant life, or most plant life doesn't like salt very much. On the other hand, if you look at the salts on Mars, many of them are sulfate salts, which were created by sulfur compounds and volcanic action in the distant past. Now, there's good evidence that the Earth had sulfate-based oceans very, very long ago, and today you only find calcium sulfate or gypsum, the stuff that plaster of Paris is made out of, from deposits left behind when it came out of the oceans. And why would that happen? It's because with a lot of oxygen, it changes the pH of the water, and it changes the way that some minerals will dissolve in it. When you have a very low oxygen environment, gypsum tends to dissolve very easily in the seawater, and when you have a high oxygen environment, there's a tipping point. You reach a certain level of oxygen, and the gypsum all comes out of solution and makes these deposits that we find like we do on the Earth. Many of the rocks are layered, and they're sedimentary rocks on Mars, and they're made of gypsum, quite a bit of gypsum. So the first thing you'll notice is the soil under your feet in some areas is quite sandy and dry, but in others it actually is quite sticky. And there's a very interesting reason for this. We've been told for a very long time that Mars is a desiccated or very, very dry planet. This isn't entirely true. Recently they discovered that it contains in the atmosphere about 10 times more moisture than theory could account for. It is super saturated with moisture. And actually there's a very good reason for that. Because the air pressure is so low, and because water boils off so easily in the low pressure and the temperatures that are present, a good fraction of the Martian atmosphere in the lower meter, the lowest layer of the atmosphere, is loaded with water. The water vapor itself forms
actually a component of the atmosphere, not just something that's dissolved in the atmosphere. So you will often see weather systems early in the mornings where frost or fog appears in the lowest meter of the atmosphere. It's like a separate layer. The lowest layer of our atmosphere is called the troposphere, and it reaches from the ground on the Earth up to about 7 to 16 kilometers. It changes with the weather conditions, and the stratosphere is a layer above that. The weather that we experience all basically happens in the troposphere, the lowest layer, right over our heads, up to the boundary to the stratosphere. The stratosphere and above, higher layers of the stratosphere, that's where the ozone layer occurs. On Mars, there is a seasonal ozone layer that shows up over the poles from time to time, but it's still pretty, ultraviolet intensive on the surface. You'll get really rapid sunburn if you spend any time exposed to the sunlight that reaches the surface of Mars. So the salts are very, very interesting, and it's because of those salts that the soil is sticky and it clumps together. Now, why is this? It's because many salts are hygroscopic, and what this means is they have the property of drawing moisture out of the surroundings. If you ever buy a product known as damp rid or something like that, and you put a box of it in your closet somewhere where there's a damp area in the house and it sucks up the moisture, and every so often you have to dump it out because it's turned into a liquid, that's a very hygroscopic salt. You may remember people would put dry rice or something like that inside their salt shakers in times past, and that's to keep the salt from caking or clumping together. And it's because it's drawing moisture out of the air all the time. If you put the rice in there, the rice is desiccated and it will absorb the moisture and keep your salt dry. Well, there's nothing like that on Mars. The soil is so loaded with salts that the moisture, which is super loaded into the atmosphere, begins to soak into the salts in the ground. The ground ends up damp and sticky, so it clumps together and it takes really good prints. Now, you can see different areas where it won't do that. So what is the upshot of it? The upshot of all of this is that with all the salts, it could be very difficult to grow crops. However, many of the salts that are present are actually very good fertilizers, and all you need to do is dilute them. The only other issue is Mars has something in the soil in some places that is a compound of chlorine and oxygen. It's called a perchlorate, and it can be very difficult for some plants and life forms to deal with. It's a powerful oxidizer like a bleach. But it doesn't exist in a lot of places, and it tends to concentrate right on the outer layer of the soil, the surface layer of the soil. And where does it come from? The ultraviolet light from the sun induces the chemistry to make those perchlorates. And perchlorates, on the other hand, are not so hard to get rid of, because if you were to do some farming, all you really would have to do is put something in the soil that would react with them. And a weak acid solution will do that. It will break it down. And in some places in the soil, there tends to be some slightly acidic material. The moisture would definitely break down perchlorates. Sawdust or composting would also do the same thing. It would break down these materials, and they wouldn't be an issue at all.
And another material that'll do it is amines, which are actually quite common in a lot of the fertilizers we would be using.
Most of the soil that was tested in the northern polar regions by the Phoenix lander showed it had a pH of about 8.5, 8.5, which is ideal for growing things like asparagus and broccoli and many other crops. Again, the salts in the soil might be an issue, and you would want to rinse it to lower those percentages. But again, many of those salts are possible fertilizers. For instance, Epsom salts, magnesium sulfate, is a large component of that. And Epsom salt is actually used because of its magnesium and its sulfur content as a fertilizer for growing plants on Earth. So that's actually not a bad thing. There are other salts as well, very few chlorides, but they do exist. So the chemistry of Mars oceans was dominated by sulfates when they were present, and not many chlorides. And most of those sulfates were the salts that I was speaking of, and gypsum. On Earth, limestone or calcium carbonate is the major component that dissolves in the seas and acts as a building material for the shells of marine life. There's also some magnesium carbonate and ends up in things like oyster shells. That's also used in fire brick, by the way. The biggest carbonates on Mars are essentially calcium carbonate and others, but they're only present in small traces. About 5% of the dust blowing in the wind on this planet tends to be carbonates. So farming on Mars wouldn't be very difficult. You'd have to have a place to trap some air, and keep the temperatures up and rinse the soil out. And if you composted a little material into it, a cupful of soil bacteria, or if you sprayed a weak sulfuric acid solution or vinegar solution in it, it would break down the perchlorates. Or if you actually just threw some sawdust in there and stirred it around, it would break them down. And you would have a great material to grow your plants in. And it would be very rich, too, because nothing has leached out the trace elements that make plants grow so well. The same reason we would often use volcanic soil on the Earth as an agricultural aid. And a lot of the soil on Mars is of volcanic origin. So we have an interesting place where growing food wouldn't be difficult, but you'd need shelter. And, a lot of people picture colonies as a bunch of cans or buildings, metal buildings on the surface. This is actually a very silly idea. If you dig into the soil, you gain a number of advantages. Number one is, just a couple of meters down, you reach a zone where the constant temperature from the geological heat keeps you at the same basic temperature all the time. So you would use geothermal or aerothermal, this is Mars, not the Earth, heating to keep your constant temperature for your living quarters. You would also gain a couple of distinct advantages by going underground. The first is you would have shielding from radiation. Soil is an inert, plentiful material that will shield radiation from space very, very easily. So if you put 1 or 2 meters of dirt on top of you, that's about between 3.3 and 6.6 feet of dirt. You would have an immense amount of shielding from any hazards like radiation from space. But the other thing is there are a lot of impact craters on Mars, and this is because it is a small planet, not much in way of atmosphere to burn up meteors before they hit the ground, and it's near the asteroid belt, so a great deal of debris ends up landing on the planet. Now realize that because its gravity is much weaker than that of the Earth, it only has about 50% of a chance that we would have on Earth for drawing in a body that will hit it. Its weaker gravity actually acts as a shield in this case. Impacts are not so energetic. On average, something striking the ground on Mars would only have about 1/8 of the energy that it would if the same body were to strike the Earth, and that's because of the difference in gravitation. But the other thing is, if you build underground, you get stable temperatures, you get shielding from radiation and heat and cold, and you also have shielding from impacts. So it makes a lot of sense to dig in underground if you're going to live on Mars. And, if you're worried about sunlight, we have fiber optics, we have mirrors, we have all sorts of ways of getting light into a building without having to have ourselves exposed to the rigors of the environment. So water, wow, let me tell you, there's a lot of water on Mars. In some places, there are glaciers right under your feet, and we can see evidence of that because as the soil warms, the water runs off and starts forming valleys or arroyos, and we see slope streaks in many areas. So by putting yourself in the right positions on Mars, in the right places, you'd have plenty of water right there. All you have to do is go out and collect the stuff, or in some cases, you can literally take the salts or the minerals and bake them in an oven and drive off enough moisture to have an endless supply. Now, it has been estimated that if you were to melt the ice on Mars that's present in the polar caps and some of the areas up in there in the northern and southern regions, there would be enough water to cover the planet 10 meters deep or more. And that doesn't sound like a dry planet to me. The water is there, and it is in a form that you need to bake it out of the soil or, cut it out of a glacier. But there is plenty of water. Now, the atmosphere is extremely thin, as mentioned before, and we can use pumps to compress that and use it as a pressure source. It's mostly carbon dioxide, over 95% carbon dioxide, but that's good for plants. And, carbon dioxide is a great source of materials for other things. We can split it electrically and make oxygen to breathe and carbon for making plastics or putting in the soil. So we have a lot of resources right there when it comes to farming on Mars. And it wouldn't take a whole lot of effort. Let's think about it. We have plenty of energy, and even solar could be used to do the job. So when we come back from the break, we're going to get into a little more about the water on Mars, where it is, what it does, and what it all means. And we'll be right back. So we have a couple of issues to talk about, and one is the water on Mars, but there's also the issue of temperature.
And that's pretty important to understand before we even start about talking about the existence and location of water. Believe it or not, Mars is actually quite a warm planet on the surface, and you often hear the temperatures quoted as ranging from minus 20 centigrade to minus 60 centigrade. Very, very chilly indeed. But understand something, and this is very, very interesting. This is the air temperature and not the surface temperature. You see, I know that you've gone outside on a fairly mild temperature day, and you've stepped on the sidewalk or the road, and it was so hot it burned your feet. And yet the air temperature was very low. On a dark surface such as a black surface or an asphalt surface or anything that absorbs a lot of sunlight, it's going to get quite hot, and it doesn't necessarily mean that the air around it will be hot as well. And the reason for this is actually very, very simple to understand. On Mars, the air is so exceptionally thin that it acts just like the space in a thermos bottle, a vacuum bottle for keeping your food warm or cold. The air layer is really an insulator. And so the ground can be very hot, can exceed 100 degrees Fahrenheit on some days on the equator, and yet the air temperature of the layer of air within a meter of it can still be extremely cold. You see, the air temperature itself has very little bearing on what happens inside the soil or at the surface of the soil on Mars. Now, what I find so fascinating is that many scientists simply go by that minus 20 to minus 60 C temperature, and they act as if that's the temperature of the ground, the planet, everything around it, and that is completely and utterly untrue. The ground temperature is high enough so that it can liquefy water that's in the soil or ice directly under the soil, and this is why we see those dark streaks, those slope streaks, is because the ground contains reservoirs of ice. Sometimes it's right on top of a glacier. And when that ground temperature seeps down to where the ice level is, it can melt that ice and it will flow out and it will darken the soil. And those slope streaks that we see are actually streaks of water flowing through the soil. That's all there is to it. So we know that the water is there, and we actually have pictures of brine lakes that exist on the surface of the planet. So now the water is available as ice in many locations, and it does come to the surface, and yes, it does evaporate away. But it is limited. It will not all boil away explosively, as you've heard. Many people say, well, liquid water on Mars would boil away in an instant and just explode into vapor, and this is absolutely wrong as well. And there are two very good reasons for that. Number one, the water is definitely, in many cases, at its boiling point. But when the water boils, the water that's left behind is cooled by that action, and it stretches out its lifespan. So evaporative cooling keeps the rest of the water in place for a while. And second, and this is very important, when the atmosphere is loaded with water vapor, no more water can evaporate at a certain point. And we see this extensively, very close to the surface, within a meter of the surface of Mars in the lower areas. And the reason is that air is a medium, just like a sponge. It has a fixed amount of volume for the water to evaporate into. And on Mars, the low pressure has allowed the water vapor itself to actually become a constituent of the local air pressure. So theory tells us that there should be a certain amount of water vapor present in the atmosphere of Mars near its surface. And what we find is that there are at least 10 times as much in those regions of evaporated water or water vapor in the atmosphere as theory predicts. In other words, the atmosphere is super saturated with moisture. And, scientists do not seem to take that into account. And there's a second reason that all of this happens, and it's very simple. And it's because of the salts in the soil. You see, we are given this impression that the water will boil away because it's so thin, the atmosphere is so thin, and the temperatures are high enough to make that happen within the soil. And if that is true, then fine. But they're referring to the table of properties for distilled water. And distilled water has very different properties, very easy to quantify properties in the laboratory. But it certainly doesn't exist on the surface of Mars because of all the salts and other chemicals in the soil. You see, these compounds act in the same way that throwing salt on a frozen road or sidewalk would act. The salt lowers the freezing point so that the water can become a liquid again.
Now, when we look at the soil of Mars, yes, during the day it gets very warm, but at night it can plunge to extremely cold temperatures. The result of that is it grows ice crystals in the soil. Now, any of you who have ever done any farming or gardening are aware of a process called frost heave. You'll go out and you'll plow a field and you'll remove all the rocks. You're getting ready to put your crops in. And the next day, after a freeze, you come back and there are new rocks in the field. And you're going, well, where the heck did these rocks come from? And the answer is very simple. Ice forms crystals or pillars underneath the soil. But at a place where it happens under the rock is driven to the surface and the small grains of soil fall into the spaces around it. So the rocks rise to the surface when the soil freezes. And the very fact that we see all these little rocks on the surface, but when they dig in, there are none underneath it, this is almost certain proof that there is water ice forming the soil at night. That frost heave is the reason for that happening. So we see visual and physical evidence for the presence of water in the soil everywhere we look on the planet. That's a fascinating piece of evidence that nobody seems to take into consideration. But it tells us that there's plenty of water there. Are the temperatures severe? Absolutely. And during the nights, it gets so cold, you really wouldn't want to be there. But that's because the air is so thin and the heat radiates readily into the sky. You know, there's a similar thing that was done by the Roman soldiers when they were on campaign thousands of years ago. They would make ice cream in the desert. And the way they did this is they would dig a hole in the sand and they would leave it exposed to the night sky all night. And then when the morning came, they'd insulate the hole and they put brass polished shield on top of it or some other shiny object. And they would keep the sun reflected off of that hole. And then when night came, they'd uncover the hole and they'd allow the heat from the bottom of the hole to radiate to the sky. And they would do this for 3 days running. And the night of the third day, it would be cold enough in the hole so that cream and honey and fruit mixed together would freeze in the bottom of the hole. And this is how the Romans made ice cream. Now, in the desert, if you've ever spent the night in the desert, you know that it gets extremely cold at night many times because the radiation from the ground radiates right away into space and is chilled immediately. And this is why. And Mars is a superior case of this happening. It has little or no insulation from its atmosphere, and the heat radiates away very rapidly at night. So you definitely would want a layer of insulation on your living quarters. And this is another reason I recommend building underground. Dig in under the soil, get your habitat underground, you get your insulation, and you're not going to have that problem. A couple of meters of dirt will give you all the insulation you need to stay comfortable. So, okay, we know that there's water in the soil, and we know that the temperatures are extreme, but we also know how to make insulators, and we also know how to make reflectors and mirrors and solar panels. This is not hard to do. It's very easy, actually, to create a system that captures the solar energy on Mars and heats a tank underground where you store your heat in water or a working fluid such as antifreeze. That can be done very easily and keep your heat going all night. And incidentally, that's just another point. On the Earth, we get about 960 watts of sunlight per square meter at noon on a good summer day. That's the highest figure you're going to get. On Mars, we get about 600 watts of sunlight on average, or about two-thirds of that. Well, this is still quite sufficient to perform a lot of functions, such as generating solar electricity or solar heat. And again, this is all just a matter of common sense and simple technology. You can gather that energy and use it, which we certainly would do. So we've covered a bit about the temperature and some of the soil conditions and living conditions and water to a point. But there are more things to know, of course. In many areas, you'll be able to extract water from a glacier or a mass of ice or even from the soil itself. And this can be done in some cases simply by shoveling it into a sealed container and heating it like an oven and baking the moisture out and condensing it, just distillation. In other places, you wouldn't have ready access to water in the form of water itself or ice, but all you'd have to do is essentially take any of the sedimentary rocks, which are calcium sulfate or gypsum, very similar to plaster of Paris, and the salts in the soil, like Epsom salt. Epsom salt is actually 51% water by mass. So if you have 100 pounds of Epsom salts in a container and you heat it up, you're going to get about 51 pounds of water out of that. And what's left is called anhydrous magnesium sulfate, and it's a material that absorbs water very easily. But my point is very simple. If you had nothing but a shovel and an oven that you can seal up, with salt and soil and ground up rock, you could get more than enough water to survive on Mars, and it is not that difficult. In fact, there are some cases where they've located craters, like one located at 70.4 degrees north. Everybody's seen this picture pretty much. I'll post it on the website. and it shows a mass of water ice in the crater that is about enough to give every man, woman, and child on Earth about 300 gallons of drinking water. And that's located in one crater on Mars. So again, there is no shortage of water. So now let's look about ourselves and see what sort of things we could get from the landscape to survive. Well, you've got iron. You've got iron all over the place. You have magnesium in the sulfate, which you could extract from metals. There are mineral resources for making things like fiberglass. You literally can take dirt, heat it up, and spin it into fiberglass right out of the sand. There are sulfates and carbonates and other materials in the soil which you can extract and break down to produce such things as semiconductors and window glass and fiberglass insulation and spun cloth, metals for making structural elements such as rebar. It isn't as if we're with a lack of resources on Mars. It's just getting the manufacturing hardware there to actually do the job. And that's what human beings are very good at. We think of ideas, we get the stuff together, and we make it happen. And by George, you know what's going to happen. People will go there. They will take 3D printers and smelters and semiconductor manufacturing hardware, and in a very short period of time, we'll have everything we need to make whole civilizations. It will grow and grow like a shot once that happens. Because Mars is an extremely habitable place in another respect. Getting off the Earth into space is an extremely expensive and difficult process, but on Mars, because the gravity is much less than that on Earth, you could get into space with a spacecraft the size of a van or an SUV and carry a couple of people. Because it is that easy to get off the surface of Mars. It doesn't take a gigantic launch vehicle like we have to have on Earth. So space travel from Mars is a piece of cake. It is an extremely easy proposition, and it would mean that we could easily get industry on and off the planet with a very small expenditure of effort and cost. I think that this alone is a huge factor that weighs in our favor for colonizing Mars. So let's, at this point, do a quick summary to cover what we've learned. Mars is about a little more than half the size of the Earth. It's about 50% farther from the Sun, only gets about 45% of the sunlight or so. Gets about 600 watts per square meter on the ground, which is useful for solar energy, compared to 960 watts per square meter for the Earth. There's ice and water in the soil everywhere, easy to harvest. We have iron and magnesium and other metal resources available. We could easily make fiberglass and insulation. We could dig into the ground to make our shelter, to give us stable temperatures, protection from radiation, and from meteorite hits from space. So living on Mars is not that difficult, and if we simply rinse the soil and do a little composting, that one word is very important, sawdust, composting, or simple chemical treatments, the soil would be suitable for growing many plants, many crops that we depend on Earth. So, and it's easy to get into space from there. It doesn't take but just a fraction of the energies to get into space from Mars that it takes to do it from the Earth. So we have a lot of advantages if we do go to Mars. Of course, there have been a lot of vehicles sent there. The robotic explorers have been all over the planet for quite a number of years. And in fact, many people jokingly refer to Mars as the only known planet that's inhabited solely by robots, which is, actually, it's true. So let's think about exactly what we'd want to find on Mars, what we would have as a goal. Setting up a splinter colony or branch of civilization just to prevent the extinction of humanity in case of a planet-wide disaster on the Earth, that alone would be reason enough to do it. But right now, due to the extremely extended travel times of about 6 to 7 months to get there, you would only be taking a one-way trip, because in that period of time, with the poor shielding we have, you'd have received half of a lethal dose of radiation from cosmic rays, and you'd be unable to return to Earth without dying of radiation poisoning in all respects. So we have to get there faster, and there are ways to do it. In the next section here, just after the break, we're going to cover some of the vehicles that landed on Mars, what they explored, and what they discovered, and when. And then we're going to get to the really important stuff here. So let's look at what we've learned, what vehicles have done it, and how we can benefit from that. Because after all, this is all about keeping humanity alive and looking at our ability to expand and find another Earth, so to speak. And we certainly have it within our capability to do that. We have the capability of altering our own Earth so it is uninhabitable. What then prevents us from admitting that we must have the technology to alter a planet to become inhabitable? And that is the question. But I also haven't raised one other question, and a lot of people want to know the answer to this one. Is there life on Mars? And we will definitely get into that in great detail very shortly here. This is Talk Universe. So the first American spacecraft to get anywhere near Mars was the Mariner 4. And this fellow was actually launched to get a reconnaissance and a few pictures of the planet. And there was no way for it to orbit it. It was simply going to fly by. Now, this is pretty amazing when you think about it, because the spacecraft was launched in November of 1964. And even then, we had the technology to build spacecraft that could reach Mars and send back significant amounts of data, which, when you stop and think about all the power, processing power you hold in your hand with a cell phone, that would far outweigh all the processing power on the planet Earth at that time. And these computers had to be hand-built. Everything was wired by hand. And they were basically unique pieces of hardware. Well, the spacecraft was sent to Mars, and it sent back the first pictures from up close, and what they saw amazed them. You see, they had often thought that Mars might have water in its environment, but the pictures they saw looked so much like the Moon that without any sort of scientific basis for it, they simply judged that it must be parched as a desert, that it must be absolutely dried out. And it wasn't until much later that the images that came back showed them huge water features, huge gullies and washes, and Valles Marineris, the largest known canyon in the entire solar system, which happens to be on Mars. But it did spur a great deal of interest, and not long after that, a program was started to send more spacecraft to Mars, send back more pictures, and eventually, in 1975, the Viking landers were built. Now, 5 of these were built, and 2 were actually launched to Mars. And the Viking landers had 2 sections each, and one was an orbiter that stayed above the planet and acted as a radio relay and a place to send and receive data. And that way, no matter where the planet is turning, no matter what you might encounter, you have the ability to relay from the planet with a low-powered transmitter to the receiver in orbit, which then had a high-powered transmitter, which sent the images and information back to Earth. And both of those orbiters were in orbit for a number of years. They maintained contact and data for 4 years and 6 years with 2 of them. And it's pretty amazing how much they discovered. Now, Viking 1 and Viking 2 also were the first landers to get on Mars and send information back from the surface, and they had some interesting results right off the bat. And years later, I happened to work at Martin Marietta Aerospace, which is now known as Lockheed Martin, and the president of the Orlando division where I was working was Walt Lowry. And Walt Lowry headed the mechanical design and development project for the Viking spacecraft and their landers when he was working in White Sands. And during a later job I had with the Science Center in Orlando, we had a Mars exhibit, and I had the great good fortune of having one of the actual Viking landers signed into my custody for 6 months, and was permitted to make any minor repairs to it as long as it didn't damage the historical value. And that was due strictly to the fact that I had worked in aerospace for over a decade by then, and knew Walt Lowry pretty well. But what an honor to have one of the actual Viking landers in your possession for a period of time like that. But that's just a side note, I digress. The Vikings sent back a great deal of information from the surface of the planet for a couple of years here and there, and they discovered the maximum winds on the surface, the maximum surface temperatures, and sent back a lot of images. Now, the rovers didn't come until much later. The Viking landers were immobile. They had to stay where they were. But they did have an arm that could reach out and grab soil samples and measure them, and they got a good idea of the soil chemistry. And they took some images from various times of day and evening, and they discovered that the surface was indeed a dried seabed or lake bottom, that the salts in the soils were pretty intense. But they also had an interesting result. The footpads had thermal measuring devices in them, and when they landed, the temperature of the footpad went down to match the temperature of the soil, and it stayed at the freezing point of water, 0 Celsius, for a number of minutes before it actually warmed up. And the reason is there actually was water ice in the soil where they landed, and as the ice started to melt from the heat of the footpad temperature would go down to the melting point or the freezing point and stay there until the ice had all melted. What an amazing discovery. Even then, they found ice on the surface of Mars with the Viking landers. And to be clear, actually, the Viking 1 lander ran for over 6 years before it failed, and the Viking 2 lander ran 3 years and 7 months, almost 4 years. So we had some very long-term data from both of those systems on the surface, and they found what appeared to be bacterial action in the soil. They had an experiment that was supposed to look for the evolution of metabolic products, such as when you eat and exhale, carbon dioxide is generated. And this labeled release experiment was designed by a Dr. Gil Levin, and it showed what appeared to be metabolic activity. Of course, NASA contested that, and it's been a long-running feud ever since then. But the fact is, nobody has ever really successfully explained how it would be what it is without the presence of bacterial metabolism. Now, to be fair, these were not the only landers to make it to Mars. Mars 2 was launched by the USSR, and it was launched in 1971, and it malfunctioned during the descent. It crashed, and the Mars 3 was launched in 71, and it landed in December. But 15 seconds after landing, its radio transmitter went out, so nobody really knows what happened after that. The Mars 6 from the USSR landed, it was launched in 1973, and it returned data during the descent, but during the landing process, it failed. The Viking 1 and 2 landed in 1976, and they were active for many years, as I stated. The Pathfinder was the next Mars mission launched from the U.S., and it was 21 years later. And it landed, and it had a rover called Sojourner. Now, this was the first little rover to land on Mars, and it drove around near the lander, which acted as a base station, and sent back a great deal of information and images. What's interesting is they named some of the features, the rocks, after things that they appeared to be like, and one of them was Barnacle Bill, which appeared to be covered with barnacles, and another rock they called Yogi, which has strange twisted patterns on it that match the patterns on brain coral. Very, very interesting finding, but nothing was made of that, but you can see some of the pictures online. They also had a thing in 1998 called the Mars Climate Orbiter, and there was a mix-up in the measurement units, and some say that it was partly metric and partly English, and whatever happened, the orbiter crashed on a Mars surface and was lost. Now, the Mars Polar Lander was launched in 1999, and they lost radio contact before landing, and they think that it crashed during the landing due to a software error. Now, Beagle 2 was from England, and that was launched in 2003, and it was going to land, and radio contact was lost before landing, and it's presumed that it crashed. Spirit and Opportunity, the two rovers we know so much about, were launched in 2003, and they landed January 4, 2004, and January 25, 2004, just a few days apart, 3 weeks apart. And Spirit roamed for almost 5 miles across the surface of Mars, and we lost radio contact in 2010, 6 years later. Now, Opportunity landed in 2004, and it's still going strong. It traveled almost 20 miles by June of 2011. It's been traveling all over the surface now for 13 years, and working very well. The Phoenix lander, launched in 2007, landed in May of 2008, and it landed near the North Polar regions of Mars, and as a matter of fact, it landed right on top of some soil. It was about 2 inches deep, on top of a glacier, a shelf of ice, and its engines, when firing on the landing, actually melted some of the ice and produced a puddle of sticky mud directly under the rover. I'm sorry, it's a lander, not a rover. It couldn't move around. And Curiosity, of course, was launched in 2011. It landed on Mars in August of 2012, and it's still running today. And the interesting thing about it is a nuclear-powered lander, and it's the largest lander to ever land on Mars, largest rover to land on Mars. It's still doing very well. And I wanted to correct the landing on Pathfinder was actually 1997, not 96. So in summary, what have we found? Well, this is the very, very interesting part. We know a lot about the soil chemistry. We know that Mars is covered in rust, and sulfate chemicals and water are the reason for that. And also, it has finally been admitted that, yes, there is a significant amount of water inside and on the surface of Mars, and that the planet actually had some very clement periods in its past. And most of the areas that we've landed have proven to be dried, muddy stream beds or lake beds or ocean beds, which was intended. They landed in those areas specifically to look for water. Now, the curious thing is, with Curiosity, it's a slightly different thing, but with the previous rovers, both Spirit and Opportunity, they were sent on what was called a follow-the-water mission. But what stands out is this. Neither rover had any method of directly measuring the presence of water, neither as a solid ice, as a liquid water itself, or as a vapor. And it seems very odd to me that a space agency would send 2 spacecraft to another world to look for water and not include on either one of them a single instrument for detecting water. There's something seriously wrong with that. What also raises a lot of questions in my mind is another very, very simple thing. Viking 1 and Viking 2 both had instruments meant to detect the presence of biology in the soil, but not a single spacecraft since then has included devices for measuring metabolism or the presence of biology. Now, you would think that with so many years of technical development and our ability to actually stuff a lot of things on a single microscope slide, self-diagnostic tools and biological measuring tools and polarizing microscopes to look for specific molecule structures, right or left-handed molecules, you would think that in all this time we would have put together some sort of a package and flown it regularly with every lander that went that would allow us to detect the presence of metabolism, something as simple as that. We have sent microscopes to Mars, or so they say, but the fact is, most of them are hand lenses, hand magnifiers. There was actually a microscope on Phoenix, but it really didn't get any use. And I often wonder why. It would not be a difficult task to locate living organisms on another planet. Even if their biochemistry was different, there are certain things that organisms do and certain structures that organisms create that would be pretty obvious to the eye. But many things have been found on Mars that look very, very organic. And in particular, what appears to be marine fossils in many cases. So a lot of people have said, well, nobody has ever identified a fossil through photography or by remote. Well, that's not true. I look at a magazine, I see photos of fossils quite often, and I know that they're fossils because if they're shot as a series of pictures of rocks in the ground and you see spiral structures in them, for instance, and they repeat over and over, you've got multiple pieces of evidence that tell you very clearly what you're looking at. And the same thing is true when you look at pictures of a beach. If you look at a beach and you see seashells, you have no doubt in your mind where those seashells came from. They're the inorganic part generated by a living organism at some point. So when you look at some of these pictures from the surface of Mars, you have to ask yourself, what the heck are these things we're looking at if they're not the remnants of organic life? And some other questions are raised. For instance, one of the major instruments used on Viking to say, well, no, there isn't any organic matter, actually is blind to less than 1 billion cells per sample, per cubic centimeter. So the instruments, the gas chromatograph mass spectrometer, or GCMS, that was sent to Mars on 2 occasions, is actually blind to organic molecules unless the stuff is literally a mass of algae or something similar. And it was incapable of detecting biology even in samples presented from common dirt. So the question is unresolved in many people's minds. But I think that if we look at the evidence in the chemistry, we see many, many signatures that include things that can only be described as the products of biology. The presence of water, even today, is a strong indicator that something, if it were alive at all, could live now. And even now, we're concerned about earthly bacteria contaminating the planet and taking over niches in any biosphere that might exist. So why do we accept the statement that there's no life on Mars when we have so much evidence that if anything had ever lived on Mars, it probably is still alive in the soil today, at least bacteria. Nothing autoclaved the planet. Now, I remember the newspaper headlines very clearly said, life found on Mars, back in 1976 when the Viking results first came back. And a couple days later it was retracted, but that's neither here nor there. We've seen these results many times over the past couple of decades. Nevertheless, there are things that appear on the planet that are clearly not just geological process results, and we're going to be looking at that in great detail in the next installation of this series. But do trust this. If anything ever lived on Mars, the conditions for it would have been adapted to, or it would have adapted to the changing conditions, and it would still be alive today. And for that reason, we have no idea what sort of biology will be in the soil of that planet now. And if we ever retrieved a sample and brought it back to Earth, we could be placing our world in dire danger. Because anything that lives on Mars is likely to have an entirely different biochemistry. Now, that would mean that viruses would have no effect on us whatsoever if they came from Mars. On the other hand, fungus, spores, bacteria, things like that, we would have no resistance to. And with that note, we would never pass out blankets from a polio ward to our children. Why in the world would we ever consider bringing back a sample from Mars that might carry live organisms? But in part 2 of this series, I'll show you strong evidence that the search for extraterrestrial life has actually been answered. This is Talk Universe.